colloid is something which has dispersed phase and dispersed medium. So what is the differentiating point of colloids? A colloid is a heterogeneous system in which one substance is dispersed. This is the dispersed phase as very fine particles that you cannot see with your naked eye in another substance called the dispersed medium. Okay, so that's the first point. If you consider the solution and disperse and colloid, they differ in particle size. So you know, in solution, particles are ions or molecules. In colloids, dispersed phase may contain particles of macromolecules like proteins or polymers and so on. Okay, that is the difference. Size. Here the small ions, small molecules, but here you have bigger macro is like a bigger molecule. Next we have colloidal particles are so colloidal particles are larger than simple molecules, but small enough to remain suspended. So they have range, I already said, 1 nanometer to 1000 nanometer, which is 10 power minus 9 to 10 power minus 6 meters. This is important. In NEET, they might directly ask you the value. Can I clear?
Yes, ma'am.
So the classification quickly let me do. See, this is very important. The table you might have learned in your, okay, you might have learned in your earlier class, but then this is important. When you have dispersed phase and dispersed medium, what is the type of colloid and example? Solid, if I have dispersed phase solid and dispersed medium is also solid, I call the solution together as solid solution. Example will be some colored glasses and gemstones. They'll have different things mixed up together. So this is one combination. Next we have solid liquid. Solid liquid. In that case, like how I said it's gold solution, like that it's simply solution. So it is paints, cell fluids. Solid and gas. You call it as aerosol. Examples are very important. They can ask you infinitely numerous questions on this table alone in different combinations. Liquid, solid, gel, cheese, butter, jellies. Liquid, liquid, emulsion. Milk, hair cream. Liquid and gas. Liquid aerosol. Fog, mist, cloud. All these are under liquid aerosols. If I have gas solid, it is again still called as solid solution. Like pumice stone, like you rub your feet and all, during bath, FOAM, foam rubber. I want to differentiate to avoid confusion. The last one is when you have gas and liquid, that is foam. And examples, I'm just writing with another color. So if you have soap, leather, forget it. Whipped cream, and froth. These two are examples under this. Can I clear the screen? You done?
Yes, ma'am.
Oh, done. Nice. So this is the classification of colloid based on the physical state of dispersed medium and dispersed phase. On basing on this, we have classified the colloids. Next, on the basis of dispersed medium. First is dispersed medium, for example, is water. Then then the name of colloidal system is going to be hydrosol or aqua sol. Sol is nothing but a short form of solution. Alcohol is alcosols. Benzene, benzosols. Air, aerosols. So there's an important thing that I want to say. Aqua dog and oil dog. These are nothing but colloidal solutions. Colloidal solution. Where of graphite in water, we call it as aqua dog, and graphite in oil, you call it as oil dog. Okay. This is sort of a point that can be asked in objective questions. So on the basis of the interaction of dispersion, phase, and medium is the third classification. Can I clear this screen?
Yes, ma'am.
Next is third classification is on the basis of the interaction of dispersed phase and dispersed medium. There are two types. Firstly, it is lyophilic colloids. Lyophilic means liquid loving solutions. Philic is loving. Liquid loving salts. They are also called as intrinsic colloids. Okay. So what happens here? The colloidal solutions now, in which the particles of dispersed phase. Here what happens? The particles of dispersed phase have great affinity for the dispersion medium. Then we call them as lyophilic colloids. Okay, these solutions are very easily formed, and also remember lyophilic colloids, they are reversible in nature. In case when water is acting as a dispersion medium, the lyophilic colloid is called hydrophilic colloid. Okay, if at all water is the dispersion medium, then lyophilic colloid will be called as hydrophilic. Common examples of lyophilic are glue, gelatin, starch, proteins, egg albumin, that is egg white, rubber, These are examples of lyophilic, very important. Next, we have lyophobic. Can I clear?
Yes, ma'am.
Next, we have lyophobic. Lyophobic is lyophobia, phobia, hate. Solvent hating colloid, extrinsic colloid. So the colloid solutions where there is, it's opposite. No, there is no affinity. No affinity between the particles of a dispersed phase and dispersed medium. You call them as lyophobic colloids. So here, actually these solutions are obviously formed, but then they're formed with great difficulty and only by special methods. So these solutions are readily precipitated or coagulated, they say, precipitated. As they have formed with great difficulty, they can be precipitated when upon addition of some small quantities of electrolytes or by heating or by shaking or doing some things, you can do it like precipitated. So further, once precipitated, they will not go back to the colloidal solution by doing any means. Okay. So what happens? These solutions are irreversible salts. Please write down that these are irreversible salts. That means these need stabilizing agents, ma'am. Stabilizing agents, if at all they want to be stable. So for example, examples of this are solutions of metals like silver and gold, aluminium hydroxide and iron hydroxide. These are going to be lyophilic colloids. Can I clear?
Yes, ma'am.
Lyophilic, obviously, solutions are more stable because lyophobic, they're not stable. We are trying to stabilize them by using different methods, putting all stabilizing agents and stuff. So lyophilic solutions are more stable than lyophobic solutions, right? So the additional stability here is because of a solvent layer around the colloidal particles. That means because there is this affinity, there is a solvent layer around the colloidal particles, and that is nothing but hydration. In lyophilic solution, what happens as there is affinity around all these colloidal particles, there is water surrounding. That's called hydration. So to coagulate a hydrophilic solution, we have to add a dehydrating agent, so that you remove the water first and then you try to do like add an electrolyte at that time and try to actually what do you say, coagulate it or anything. So yeah, anyways, lyophilic are more stable than lyophobic solutions for that reason. So I'm clearing it. Next, so lyophilic and lyophobic, there is so much of difference between them. I just want you to write down some of them. Lyophilic and lyophobic. Lyophilic, I'm not writing, I'm just lyophobic. I'm writing only the keywords and you can just write down as statements. First one, these are formed by direct mixing. Okay. Whereas these are formed by special methods. As I said, lyophobic, they won't easily, they don't have affinity. So they are mixed by special methods. And this is reversible in nature. And this is irreversible in nature. Okay. Here, the particles are true molecules, but they are big in size. Particles are big in size. Whereas these particles are aggregates of many molecules. Aggregates of many molecules. Stability, if I want to talk about, these are very stable. Next is unstable. They require some amounts of stabilizers. No effect on the action of electrolytes. Here, addition of electrolytes leads to causes precipitation. Next, part very important, like we're covering almost everything. These particles do not carry any charge. Okay, whereas these particles move in a specific direction. They move in a specific direction, either towards anode or cathode, depending on their charge in electric field. I'm clearing the first 3 points. The 7th point would be See here, the particles are heavily hydrated. Obviously, why? Due to attraction of solvent. Due to the attraction for the solvent by solute. Particles of these types of colloids are not hydrated. Okay. 8. They precipitate may or may not migrate. So if you know, they do not show Tyndall effect. They do not show Tyndall effect. They show Tyndall effect. Last. 9th. Examples we are talking about. The examples here are mostly organic in nature. Mostly organic in nature. Like starch and gelatin, I already wrote the examples. So again, the 9th point here. 9th point here is inorganic in nature, that is transition metal salts in water, gold, etc., and metal solutions. Nine points sort of covers almost all the differences. If you're done, I am clearing. I'll be clearing this.
Done, ma'am.
Right. So the 4th classification of colloids is on basis of chemical combination, chemical composition, chemical composition. So what happened now? According to the chemical composition, we have seen they are classified as inorganic colloids and organic colloids. So inorganic colloids means we have metal salts like copper, silver, gold, platinum salts. Non-metal solutions like sulfur, iodine, graphite. Solution of oxide and hydroxide are SNO2, TiO2, Fe2O3, FeOH thrice, AlOH thrice, chromium hydroxide. D. Salt solutions, that is silver bromide, silver iodide, arsenic 2S3, etc. Organic colloids, I have homopolar solution. That means particles carry similar type of charge like solution of rubber in benzene, which contain negative charge colloidal particles of latex. Rubber is latex only. Next is hydroxy solution, and that is starch solution. That's it. Under this, the second one is hydroxy solution, which is starch solution. This is the fourth that is under on the basis of chemical composition. Can I clear? I'm clearing it, okay? Is anyone still copying? No, right?
No, ma'am.
Okay. The fifth one. On basis of charge on particles. First, positive salts, negative salts. Under positive salts, it is metal oxide and hydroxide. Under this, again the same SNO2, TiO2, exactly same like those solution of oxide and hydroxide only. ALOH thrice, FeOH thrice, CrOH thrice. Basic dyes. Methylene blue, Bismarck brown, these are colors. Negative salts mein you have metal salts, which is AgAuPtCu. Next is acidic dye, Congo red, erosive. Sulfide salt, cadmium sulfide high, mercury sulfide, As2S3, Sp2S3. Natural salt, blood, clay, charcoal, latex, rubber, smoke, gum. So you could see under negative salts 4 types. That's on the basis of the charge on particles. Last we have on the basis of the types of particles of dispersed phase. Okay, I'm clearing it. So on the basis of types of particles of dispersed phase, we have multimolecular, macromolecular, and associated colloids. What are they? Multimolecular, macromolecular, associated colloids. Okay. So first, let me start with multimolecular. So multimolecular means they have aggregate of atoms, or they have small molecules less than 1 nanometer size. For example, solution of gold atoms and sulfur molecules. In these colloids, the particles are held together by van der Waals forces. Macromolecular. So in this types, the particles of dispersed phase, they are sufficiently big in size. They are sufficiently big in size to be of a colloidal particles, of a colloidal particle. So what happens, these macromolecules, they form the dispersed phase, and mostly this happens by in like polymers with high molecular masses. Then that is possible. So these are actually quite stable. They resemble true solutions in many respects, like the starch, cellulose, proteins, enzymes, gelatin, etc. Associated colloids are nothing but micelles that you might have noticed. These substances, they actually are normal strong electrolytes at low concentrations. See, these are strong electrolytes at low concentration. That behave as colloidal particles at high concentration. Like soap. See, if you remember the micelles. Micelles, no, they're very small structures. They have this hydrophilic head and so on, if you remember. Like exactly in soap, you might have learned in some chapter in carbon and its compounds or something. The cleansing action of soap. Examples of micelles are those sodium stearate, all of those.
Yes, ma'am.
So if we have copied this part, let's see if we can once talk about quickly the cleansing action of soap. There are two things that we have to learn in this micelles part. One is the Kraft temperature, the other one is critical micelles concentration. These two terms have to be understood. So can I clear the screen?
Yes, ma'am.
Nice. So micelles are small spherical structures. They are composed of a lot of thousands of molecules. Okay. So the formation of micelles actually need particular temperature. The formation of micelles take place only at particular temperature. That temperature is called Kraft temperature. The other one is the concentration above which micelle formation becomes appreciable is termed as critical micelles concentration. What do you mean by this is, so its value depends on nature of the dispersed phase and medium. So surface active agents like soaps and detergents, they form micelles. Beyond soaps and detergents, they form micelles beyond critical micelle concentration 10 power minus 3 mole per liter. Very important point is, usually longer the hydrophobic chain, smaller is the CMC. First point. Second, CMC increases with decreasing polarity of the dispersion medium. So we have, I hope you know, soap solution. Soap is basically a sodium salt of any fatty acid. It is generally represented as RCOONA. Like sodium stearate is nothing but sodium stearate is C17H35COONA. So we say you dissociate this into this minus ion and this plus ion. Okay, so when dissolved in water, it's going to dissociate into RCOO minus and Na plus ions. Again, RCOO minus ions, and they consist of a long hydrocarbon chain, which is a hydrophobic, water repelling, and a polar group COO. This is hydrophilic. So, hydrophilic, for example, there's a micelle formed, all of which is COO minus Na, COO minus Na plus, COO minus Na plus. So all of this will be exactly formed in this way only. It's an aggregate of all these ions, and there is a bulk of all of this form, an aggregate of all of these. Their hydrocarbon chains are pointing towards the center with the COO minus part remaining outside. So whichever is there, they're able to combine and form COO-Na. The others are aggregate. This the whole in between is called the micelle. They have so many like micelles forming. So sodium stearate in the soap is a micelle. Sodium lauryl sulfate in a detergent, and cetyl trimethyl ammonium bromide also in detergent. With this part, I don't know if you have learned. I'm clearing the screen. Cleansing action, I don't think so. We need to do now because you might have already done. So how do we prepare the colloids? That's the important next thing that you have to learn. That is preparation. Of what? Of lyophobic colloids. What are the preparation methods? First is condensation method. In condensation methods, what are these condensation methods? See, particles of atomic or molecular size, they are induced to combine to form aggregates having colloidal dimension. So what happens here? What will happen? Particles of atomic or molecular size, they are induced. We are preparing them. They are induced to combine to form the aggregates that are required for the colloid, having dimensions of a colloid. So for this, we have chemical and physical methods also to do this. If it is chemical method means colloidal solutions can actually be prepared by double decomposition, oxidation, everything. So let me go in the order. So when a hot aqueous dilute solution of As2O3, which is arsenic oxide, is mixed with hydrogen sulfide in water, then As2S3 is obtained. Okay. So again, if you want to write this, see, by the name itself, you know the equation. It is actually As2O3 reacting with H2S, and on double decomposition, this is forming. And the second, I'm clearing the above part. Under lyophilic, under condensation, under chemical method, under double decomposition, I wrote the equation. Under chemical method, the B part is oxidation. A colloid solution of, okay, I'll write me at SO2 plus, sorry, I'm taking so much time. This will be the last. SO2 plus 2H2S on oxidation is giving 3S plus water. Also 2H2S plus bromine is giving rise to 2HBr aqueous. Wherever I write S solution, that is only the colloid. That is the B. Under chemical methods, that is the B. After double decomposition, this is oxidation. Next you have, quickly I'll complete the chemical part alone. Reduction, hydrolysis. So what will follow? Colloidal solutions of gold and silver, they are obtained by this. 2AuCl3, formaldehyde, water gives you Au solution, formic acid, and hydrogen chloride. This solution of gold is also called as purple of gaseous photoster. Hydrolysis. So here FeCl3 plus water gives rise to FeOH thrice solution plus HCl. That means solution of metal hydroxides can be obtained through this method. So similarly, the other AlOH thrice also same. AlCl3, water, aluminium hydroxide, HCl, same. Same. This is the chemical methods. I'm going to continue with the physical methods in the next class. Mostly by next class. Oh no, we have so. Or by the other class. In this week, we will definitely complete the surface chemistry chapter. Okay. So I'll see you all in the next class. I'll be continuing with the preparation of Lyophobic colloids with the physical methods. If you all have copied, you can leave the class. I'll see you again on Thursday. Thank you and good night. If you all have copied, I'm just ending the session. Thank you.